Right, let's use mathematical induction to prove that the sum from I equals 2 to n of 2 to the I minus 1 is equal to 2 times 2 to the n minus 1 minus 1 for all positive values of n, and n is greater than 1. Now you need to be careful. Your initial value, an integer greater than 1, means we're going to be starting at 2. Very important that you read your initial conditions correctly. So required to prove that the sum from I equals 2 to n of 2 to the I minus 1 is 2 times 2 to the n minus 1 minus 1 for all n positive integers, and n is greater than or equal to 2. So now our proof, well, our initial statement says we need to prove statement is true for n equals 2. Okay, so our left-hand side says that 2 to the I minus 1 is equal to 2 to the 2 minus 1, which is equal to 2. And our right-hand side, which is 2 times 2 to the n minus 1 minus 1, is going to be 2 to the 2 minus 1 minus 1 is 2 to the 1, which is 2, minus 1 is 2, and that's equal to my left-hand side. So therefore, my statement is true for n equals 2. My next step says I need to assume that it will be true for n equals k. So assume statement is true for n equals k. So in other words, what I'm saying is that the sum from I equals 2 to k, now instead of n, of 2 to the I minus 1 is 2 times 2 to the k minus 1 minus 1. All right, then my final step is I'm going to prove, so required to prove that my statement is true for n equals k plus 1. So in other words, I want that I equals 2 to k plus 1 of 2 to the I 1 is 2 times 2 to the k plus 1 minus 1 minus 1. Okay, so let's have a look. Maybe we can just add a little bit to, because 1 minus 1 is just 2 to the k. Okay, so let's have a look at our left-hand side, and maybe I'll go up here and say, well, our left-hand side is I equals 2 to k plus 1 of 2 to the I minus 1. And we know that we summed up to k and then we added the next one. So I could have written that as my sum from I equals 2 to k of 2 to the I minus 1 plus 2 to the k plus 1 minus 1. So that's my next term, right? And this part over here was my inductive hypothesis, and we assumed that was going to be true. So this over here, the 2 to the 2k minus 1 minus 1 can be put in. So 2 to the 2k minus 1 minus 1 plus 2 to the k plus 1 minus 1 is 0, and that we can say we're using the inductive hypothesis. And now it is a case of playing with it, rearranging it, and trying to get it into the correct form. So knowing my exponent laws, maybe I can expand first. So 2 times 2 to the k minus 1 minus 2 plus 2 to the k, and 2 times 2 to the k times 2 to the negative 1 minus 2 plus 2 to the k. And 2 times 2 to the negative 1 cancel each other out. So that means I've just got 2 to the k minus 2 plus 2 to the k. And of course, 2 to the k plus 2 to the k is 2 times 2 to the k. And I can take out a common 2, so it's 2 to the k minus 1. And I go back and I think, oh, good, that's my right-hand side. So that's equal to my right-hand side. So therefore, my statement is true for n equals k plus 1. And then I can say, hence, statement is true for n equals 2, 3, 4, k plus 1. Therefore, by mathematical induction, my statement is true for all positive integers n greater than 1.